Okay, the first application of equilibria that we're going to talk about is solubility. And specifically, we're going to be talking about KSP, the common ion effect, and solving equilibrium expressions where X is negligible. Okay, so you may remember from general chemistry we talked about solubility rules. And with solubility rules, we were talking about how to predict whether or not a precipitate would form. So for KSP, we're typically, for this section, we're often going to be talking about quote-unquote insoluble salts. But remember, now that we're talking about equilibria, there's a very small amount that will dissolve back into solution. So for example, common insoluble compounds are things with like calcium hydroxide is insoluble. But a very small amount of it will dissolve back into solution, and we can predict that using our KSP. So we are going to call this equilibria of slightly soluble or insoluble ionic compounds. So again, any insoluble ionic compound is actually slightly soluble in aqueous solution. So there's a very small amount of this compound that will dissolve and dissociate completely. For a slightly soluble ionic compound in water, you have an equilibrium between the solid and the aqueous ions. And if we're talking about the reaction quotient, which is equal to our equilibrium constant at equilibrium, we just say that it's our products. So a concentration of Pb times the concentration of F minus. This is squared because we've got the 2 out in front. And we don't include this solid because it's a pure solid. So this is our entire equilibrium or Q expression. So for pretty much, actually for all of our KSP expressions, we're going to be talking about Kc, so equilibrium in terms of concentration. So this is called the ion product expression for a slightly soluble ionic compound. And the SP, what this stands for is solubility product. So KSP is our solubility product constant, but it's just our equilibrium constant specific for solubility. And the higher our KSP value, the more soluble our salt. So here's a variety of KSP values. So we have some really small KSP values, like silver sulfide is 10 to the negative 48th, so it's really, really tiny. So very little silver sulfide will dissolve in aqueous solution. And then we have other insoluble salts that are still classified as insoluble, but they have a much higher KSP, such as lead 2 fluoride. Okay, so I want to show you an example. So here's lead 2 sulfate is the key component in lead acid car batteries. Its solubility in water is 4.25 times 10 to the negative 3rd grams per 100 milliliter solution. What's the KSP of PbSO4? Okay, so when you're doing a problem like this, always first step in any equilibrium problem is always write the balanced chemical process of the equilibria. So we have PbSO4 that's dissociating to form Pb2 plus SO4 2 minus. So our KSP expression is just equal to the concentration of Pb2 plus, and remember this is in molarity, it's our standard state for Kc expression, plus our sulfate, and they're both raised to the first power because the coefficient in front is 1. Okay, so we know what the concentration is at equilibrium. So if we were going to do an ice table, we would say we initially have some amount of this, we have nothing of these, we lose, for every 1 mole of PbSO4, we gain 1 mole of Pb2 plus and 1 mole of SO4 2 minus. So this change, this is our solubility, or it's the amount, the number of moles of PbSO4 that are dissolving in water. So this X is, so sometimes books will call this S. Okay, so for our equilibrium expression, we can say that our KSP is equal to X squared, or sometimes you'll see this as S squared, so our solubility squared. Okay, we know what our solubility is, but it's not in molarity, so we need to convert this to molarity. So our solubility is equal to 4.25 times 10 to the negative third grams per 100 milliliters. And we need to divide this by the molecular weight, which is roughly 303 grams in 1 mole of PbSO4. And then we also know that for every 1 liter, we have 1,000 milliliters. So our milliliters cancel out, our grams cancel out, and we're left in moles per liter, or molarity. And you should get 1.40 times 10 to the negative fourth molarity. So that's our solubility. So now we can plug this into our KSP expression. We've got 1.40 times 10 to the negative 4 molar times 1.40 times 10 to the negative 4 molar. And if we multiply that out, we get 1.96 times 10 to the negative 8th. So this is our KSP for lead sulfate. I just want to show you another example. Calcium hydroxide, or lime, is a major component of cement, and calcium hydroxide solutions are used in industry. So for this problem, we're just going to calculate the molar solubility of calcium hydroxide knowing the KSP. So this is kind of going the other direction. So again, always start by writing out that balanced equation. So it's calcium hydroxide, solid, dissolving to form calcium 2 plus 2 OH minus. And again, initially we have some solid amount of calcium hydroxide. We don't have any calcium 2 plus or hydroxide. Our change is negative X, or you can call this our solubility. And then we get plus X here and plus 2X for our hydroxide. And our KSP expression is going to be calcium 2 plus times OH squared, because of this 2 out in front. So for our equilibrium expression, we're going to say that KSP is equal to X times 2X squared, which is 4X cubed. So here's another way of looking at it. So again, we have our KSP expression, and here they've written it in terms of S for solubility. So 4S cubed is equal to the KSP, which is 6.5 times 10 to the negative third. Divide 4 on both sides, and then you have to take the cubed root to get the solubility. And you get that the solubility is 1.2 times 10 to the negative second molar.